What if I told you that a three-man garage operation running out of a converted barn in Ohio discovered something that McLaren, Ferrari, and Mercedes all missed? Not through million-dollar wind tunnels or supercomputers, but with a borrowed dynamometer, some welding equipment, and an approach so unconventional that professional race engineers literally laughed when they saw it. This is the story of how conventional wisdom in racing got turned on its head by people who couldn't afford to think conventionally. And here's the thing. This isn't just a racing story. This is a story about what happens when desperation meets creativity, when expertise becomes a cage, and when three broke guys from the Midwest accidentally rewrote the rulebook that billion-dollar motorsport programs had been following for decades. This is Legacy Engines, and I spend way too much time thinking about the moments in motorsport history where everything we thought we knew got flipped upside down. If you're someone who loves the intersection of engineering, underdog stories, and the kind of technical rabbit holes that make you question everything you thought you understood about going fast, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Now, before we get into the meat of this, I want you to picture something. It's March 2019 at Sebring International Raceway. The who's who of endurance racing are there. Factory teams with semi-trucks full of spare parts. Armies of engineers staring at telemetry screens, drivers who've won Le Mans. And then there's Midwest Motorsports Dynamics rolling up in a converted RV, towing a trailer they bought used off Craigslist. Their entire race budget for the season was less than what Porsche spent on catering that weekend. The paddock talk started immediately. Veterans pointed and snickered at their setup. The car, a modified Ligier JSP 320 they'd bought as a write-off from a crash, looked wrong to trained eyes. The rake angle was all off. The spring rates made no sense. The damper settings violated everything taught in vehicle dynamics textbooks. One engineer from a rival team was overheard saying it looked like someone had set the car up using a smartphone app. He wasn't entirely wrong. But what nobody knew was that this wasn't ignorance. It was revolution. You see, Mark Dennis, Jim Catalano, and Terry Washington weren't stupid. They were broke. And being broke in motorsport forces you to think differently. Dennis had spent 15 years as a suspension technician at various IMSA teams before getting laid off when his team lost sponsorship. Catalano was a mechanical engineer who'd been designing agricultural equipment until the company moved operations overseas. Washington ran a small machine shop that mostly made parts for local factories. Together, they had about $200,000, a barn, and an idea that everyone said was insane. Here's where it gets really interesting. In traditional racing setup philosophy, the kind taught at every racing school and used by every professional team, you're working from decades of accumulated wisdom. You start with spring rates calculated from corner weights and expected G-forces. You set your ride height based on aerodynamic efficiency. You adjust dampers to control weight transfer rates. Anti-roll bars balance the car through corners. Toe and camber settings follow established curves based on tire data. It's systematic. It's proven. It works. But Dennis had noticed something during his years in the paddock. Every team was converging on essentially the same setups. Sure, there were minor variations, but everyone was working from the same playbook, the same simulation software, the same tire models, the same fundamental assumptions about what makes a car fast. And here's the thing. When everyone thinks the same way, everyone hits the same walls. The conventional approach assumes you're optimizing individual parameters toward theoretical ideals. Spring rates that give you the right ride frequency. Dampers that control oscillation within specific bounds. Roll stiffness distributed to match the car's weight distribution. Alignment that maximizes tire contact patch through the corner. It's all very logical, very scientific, and very expensive to get exactly right. According to a 2021 analysis published by Motorsport Analytics Quarterly, the top 10 IMSA teams spent an average of $3.2 million annually on simulation and setup development alone. $3.2 million to converge on setups that, at the top level, differed from each other by margins that could be measured in millimeters and fractions of a pound per inch. But what if the entire approach was asking the wrong question? What if optimizing individual parameters to theoretical perfection was actually the problem, not the solution? The birth of what would later be called the Dennis method started in 2018, 6 months after Mark lost his job. He was in his garage staring at suspension data he'd accumulated over his career, general setup sheets and telemetry from various cars he'd worked on. Something bothered him. Cars with theoretically inferior setups would occasionally post competitive lap times. Not often, but enough to notice. These outliers were always dismissed as flukes. Driver having a good day, track conditions suiting that particular setup. Statistical noise. But Dennis started plotting these outliers, looking for patterns that everyone else had ignored. And he found something that would consume the next year of his life. The fast outlier setups had no consistency in their individual parameters. Spring rates all over the map, ride heights that varied wildly, damper settings that seemed almost random, but they had one thing in common that nobody had ever measured, because nobody had ever thought to measure it: the relationship between front and rear natural frequencies under combined loading conditions, not static conditions, dynamic ones, real driving conditions. Braking, accelerating, cornering, often all at once. Let me explain that in plain terms, because this is the part where most people's eyes glaze over, and I refuse to let that happen. Every suspension system has a natural frequency. Think of it like a tuning fork. Hit it, and it vibrates at a specific rate. Your car's suspension does the same thing. Hit a bump, and the suspension oscillates at a rate determined by the spring rate and the weight it's carrying. Traditional setup philosophy says you want the front and rear frequencies within a certain range of each other, typically measured in static conditions, sitting still in the garage. Front frequency here, rear frequency there, keep them close enough, and the car should handle predictably. But Dennis realized something that seems obvious in hindsight, but had never been formally explored in motorsport. Under real driving conditions, these frequencies shift dramatically. And more importantly, they interact with each other in ways that nobody was modeling, nobody was measuring, and nobody was even looking for. The front suspension isn't just oscillating on its own, it's oscillating in relationship to the rear suspension. And depending on the setup, those oscillations can either amplify each other or cancel each other out. Now you might be thinking, okay, that sounds interesting. But is it actually significant? Here's what most people don't realize. The difference between those two outcomes, amplification versus cancellation, is the difference between a car that degrades over a race stint and one that doesn't. A car where the oscillations amplify each other becomes progressively harder to drive as conditions change. Fuel burns off, tires wear, track temperature shifts, and suddenly the setup that worked in qualifying is fighting the driver instead of helping them. A car where the oscillations cancel each other out maintains its behavior regardless of those changing conditions. It doesn't get better necessarily, but it doesn't get worse. And in endurance racing, not getting worse is worth more than you can possibly imagine. Think of it like noise-canceling headphones. You know how they work? They produce a sound wave that's exactly opposite to the ambient noise around you. And the two waves cancel each other out. Silence. What Dennis discovered was that certain suspension configurations created a similar phenomenon. The front and rear suspension oscillations would meet under dynamic loading and destructively interfere with each other, canceling out the unwanted chassis motions that normally build up over a race stint. The car would hit a bump that should have upset it, and nothing would happen. The oscillation just disappeared. The chassis stayed stable. The driver could maintain their reference points lap after lap. The problem, and this is a significant problem, was that you couldn't calculate this with traditional methods. The interactions were too complex, too dependent on dynamic conditions that varied constantly. The simulation software that teams spent millions of dollars on didn't model it because nobody knew to look for it. You couldn't derive the optimal setup from first principles. The only way to find these magic combinations was through exhaustive physical testing, testing thousands of configurations until the patterns emerged from the data. And that kind of exhaustive testing normally costs an astronomical amount of money. Unless, of course, you get creative. This is where Jim Catalano enters the picture in a way that nobody could have predicted. Remember, he'd spent his career designing agricultural equipment, combines, tractors, machines that had to function on wildly varying terrain, where the ground surface changed every few feet, and no 2 days were ever the same. The agriculture industry, out of pure financial necessity, had developed some genuinely fascinating approaches to suspension dynamics that motorsport had never considered. Why? Because racing happens on relatively smooth, predictable surfaces. Farm equipment has to function in chaos. The engineering problems sound different, but at a fundamental level, they're asking the same question. How do you maintain consistent performance when the inputs are constantly changing? Catalano had worked on self-leveling systems that used predictive algorithms to adjust suspension behavior in real time. More relevantly, he developed methods for testing suspension performance using accelerometers and basic data logging equipment that cost a few $100s instead of the hundreds of thousands that professional racing teams spent on their data acquisition systems. Agricultural engineers had to be cheap. Their customers were farmers watching every dollar, not factory racing teams with corporate backing. The frugality of agricultural engineering had produced genuinely elegant solutions that the better-funded world of motorsport had never bothered to look at. When Dennis shared his frequency interaction theory with Catalano, something clicked immediately. Catalano recognized the phenomenon from his agricultural work. He'd seen similar harmonic interactions in combine harvester suspension systems, where the threshing mechanism's vibration frequency would either amplify or dampen the suspension's response to terrain irregularities. The farmers didn't know why some machines ran smoother over rough ground than others with theoretically superior specifications. Catalano had known why. He just hadn't connected it to racing until that conversation in Dennis's garage. Together, they started developing what Catalano called a resonance mapping methodology. Instead of starting with a target setup and optimizing toward it, they would systematically test the entire available setup space, mapping where the destructive interference patterns emerged. It was a fundamentally different approach, not optimization toward a known target, but exploration of an unknown landscape. They weren't trying to build the theoretically perfect setup. They were trying to find the hidden pockets of stability that traditional methods couldn't even see. But theory doesn't win races. They needed a car, a real car they could instrument and test. They needed to prove that this phenomenon existed in a real racing vehicle under real conditions, not just in data from old sessions or agricultural test rigs. That's when Terry Washington joined the picture. His machine shop was struggling in the way that small American manufacturing businesses had been struggling for years, watching work disappear to cheaper overseas competitors. He was looking for something new, something that used his fabrication skills in a way that actually excited him again. Washington brought two things to the partnership that Dennis and Catalano couldn't provide. First, genuine world-class fabrication ability. The man could build or modify virtually anything from raw metal, and do it with a precision that would have cost a fortune at a professional race shop. Second, and more practically important in the short term, he had a dynamometer. A 20-year-old engine dynamometer he'd bought from a closing speed shop. Not exactly cutting edge, but functional. With some modification and the addition of Catalano's agricultural-grade accelerometer systems, it became the foundation of their entire testing program. In October 2018, they pooled their resources and bought the wrecked Ligier. The previous owner, a gentleman driver who'd stuffed it into the wall at Road Atlanta, practically gave it away. The tub was structurally sound, but everything else needed work. For most people, that would be a problem. For three guys with fabrication skills, time, and a specific experimental agenda, it was perfect. They weren't trying to restore the car to factory specification. They were trying to use it as a test bed for something nobody had ever tried before. The testing process they designed was, by any conventional measure, Completely insane. Washington covered his shop floor with industrial rollers salvaged from a closed factory, creating a crude but functional rolling road beneath the stationary car. The Ligier sat on these rollers, engine running, while the suspension cycled through loads that simulated the combined forces of cornering, braking, and acceleration. Accelerometers were taped to every suspension component, every corner of the chassis, every location where useful data might emerge. Catalano's agricultural data logging equipment recorded everything. And then they'd change the setup and do it again, and again, and again. The configurations they tested weren't random. Catalano had developed an algorithm based on his agricultural work that identified the most promising regions of the setup space to explore, narrowing thousands of possible combinations down to the ones most likely to produce the destructive interference pattern they were looking for. Even with that filtering, they tested over 4,000 distinct configurations across 3 months of 12-hour days, 7 days a week. The neighbors thought they were running some kind of underground operation, hearing the engine screaming in the barn at all hours of the night. What they were actually running was the most comprehensive suspension research program that had ever been conducted on a budget that wouldn't cover a single day of testing for a factory team. Here's what most people don't realize about that testing process. The data they were generating was meaningless to anyone using conventional analysis methods. If you'd handed their setup sheets to any professional race engineer during those 3 months, they would have looked at the numbers and told you the car was undrivable. Spring rates that were too stiff in some configurations, too soft in others, with no apparent logic connecting them. Ride heights that violated aerodynamic efficiency principles. Damper settings that seemed to contradict each other from one test to the next. The entire dataset looked like noise. But Catalano wasn't looking for what traditional engineers looked for. He was looking for the moments when the accelerometer data from the front of the car and the accelerometer data from the rear of the car produced specific phase relationships, moments when the oscillations lined up in exactly the wrong way to reinforce each other, and exactly the right way to cancel each other out. By February 2019, they had identified 12 setup configurations that showed genuinely promising interference patterns on the rollers. But here's the thing about laboratory testing. Whether your laboratory costs $50 million or is a converted barn in Ohio, it only tells you so much. The real world is always more complicated than the model. Track surfaces have textures and temperatures that rollers can't replicate. Aerodynamic loads change the suspension's behavior in ways that static testing misses. The driver's inputs create their own dynamic interactions with the chassis. They needed track time, and track time costs money they didn't have. So they did what broke racers have always done. They entered small events where the entry fees were manageable and the competition wasn't paying close enough attention to notice what they were actually doing. NASA endurance races, regional club events, low-profile weekends where a privateer team running a rebuilt wreck wouldn't attract scrutiny. They weren't there to race. They were there to gather data. Every stint was an instrumented test session disguised as a race entry. Other competitors saw a slow, oddly set-up car making up the numbers. Dennis, Catalano, and Washington saw a moving laboratory generating irreplaceable real-world data. The results from those early events started revealing something extraordinary, and this is where the story takes a turn that even Dennis hadn't fully anticipated. Their theoretical lap times, calculated using conventional methods based on their spring rates and ride heights, suggested they should be 3 to 4 seconds off the pace of properly set up cars and similar machinery. Instead, they were within a second. Not faster, not yet, but dramatically closer than the setup specifications had any right to produce. And more importantly, there was the consistency. While other cars in those events varied by 2 or 3 seconds per lap as conditions evolved through a stint, the Midwest Motorsports car varied by half a second at most. Lap after lap, stint after stint, the times barely moved. Now, I want to stop here for a second, because I think it's worth really understanding what that consistency actually means in practice. Look, in sprint racing, consistency matters less. You qualify fast, you race hard, You manage the tires for 40 minutes, and it's done. But endurance racing operates on completely different mathematics. A car that laps consistently 1 second slower than its peak will cover more distance in 4 hours than a car that starts 1 second faster but degrades by 2 seconds over that same period. The math isn't complicated, but its implications are profound. Consistent pace isn't a consolation prize for not being fast enough. In endurance racing, consistent pace is the fastest way to win. Dennis had understood this intellectually from his years in the paddock. He'd seen teams throw away victories by chasing peak lap time at the expense of consistency. But seeing it emerge from his own data, watching the Midwest car maintain its pace while everything around it degraded, transformed his understanding from intellectual to visceral. This wasn't just a theoretical advantage, it was a measurable, repeatable, exploitable performance edge. And now they needed to prove it in a context that the motorsport world would actually notice. The decision to enter the IMSA Michelin Pilot Challenge race at Sebring was simultaneously bold and practical. Bold because Sebring is one of the most demanding tracks in North America, notoriously rough, physically brutal on cars and drivers, with a 4-hour race distance that separates genuine performance from machinery that merely looks fast. Practical because Sebring's specific characteristics, the bumps, the concrete patches, the transitions that upset suspension systems, were precisely the conditions where their frequency interaction setup should show its greatest advantage. If the destructive interference principle worked anywhere, it worked at Sebring. The scrutineers who inspected the car before the race were visibly confused. Everything was legal. Nothing made sense. The front springs were running at 800 pounds per inch, stiffer than any comparable car in the field. The rear ride height was 15 millimeters higher than the aerodynamic optimum. The front anti-roll bar was completely disconnected. One official pulled Dennis aside and asked quietly whether they needed assistance with the setup, genuinely concerned that something had gone wrong during transport. Dennis thanked him and said they were good. The official walked away looking unconvinced. Practice sessions generated exactly the kind of attention they'd expected, and not the flattering kind. The car looked wrong in motion. Visually wrong, the kind of wrong that makes experienced observers uncomfortable, because their pattern recognition is screaming that what they're seeing shouldn't be happening. The nose ran too high. The rear squatted dramatically under acceleration. Through direction changes, the car rolled in a way that made veterans wince. A data engineer from one of the Porsche factory efforts pulled their telemetry from the timing screens and used it in a presentation to his drivers as a textbook example of what poor setup looked like. He pointed to the suspension travel histograms and explained exactly why those numbers indicated a car that would be slow and inconsistent. He was right about everything except the conclusion. Here's what that Porsche engineer didn't know, and this is where it gets really interesting. The visual cues that experienced observers use to evaluate a racing car's setup are calibrated to conventional setups. When we see a car rolling through a corner, our pattern recognition says that's bad, because in a conventionally set up car, that roll represents energy being wasted, weight transfer happening too slowly, tires operating outside their optimal range. But the Midwest car wasn't a conventionally set up car. The roll he was seeing wasn't uncontrolled. It was managed. The frequency interaction between front and rear suspension meant that the chassis movements, which looked alarming from outside the car, were actually being absorbed and cancelled before they could affect the tire contact patches in the way that conventional roll would. The car looked loose. It was actually more controlled than anything else in the paddock. The difference was that its control mechanism was invisible to conventional analysis, operating at a frequency and through an interaction that nobody was measuring, because nobody had thought to look for it. The Porsche engineer's presentation was technically flawless and completely wrong, because he was applying the right analytical framework to the wrong type of car. Qualifying was where things started to get genuinely weird, and I mean that in the best possible way. In a field of 38 cars, Midwest Motorsports qualified 15th. Not a headline result. Not the kind of performance that gets replayed on highlight reels or generates breathless commentary from the broadcast team. But for anyone paying close attention to the specific numbers behind that 15th place, something didn't add up. The Porsche engineer who'd used their telemetry as a cautionary tale pulled their speed trap data from the timing screens and found exactly what he expected. They were slow in a straight line. The high ride height and disconnected front anti-roll bar created aerodynamic drag that cost them approximately 5 miles per hour on Sebring's back straight compared to similarly powered cars. Straight-line speed deficit confirmed. Setup criticism validated. Case closed. Except the minimum corner speeds told a completely different story. Through the carousel, one of Sebring's slowest and most technically demanding corners, the Midwest car was carrying 4 miles per hour more than cars with significantly more power and significantly more sophisticated setups. 4 miles per hour in a corner that's slow isn't a rounding error. It's not driver bravado or a single hot lap anomaly. It's a fundamental handling characteristic. It means the car is generating more mechanical grip through that specific corner than physics should allow given its setup specifications. The Porsche engineer stared at that number for a long time. Then he went and found his team's chief engineer and showed it to him without saying anything. The chief engineer stared at it too. Neither of them said anything for a while. What they were looking at was the frequency interaction principle in action, though they didn't have that language yet. The carousel at Sebring is a corner that rewards suspension stability above almost everything else. It's slow enough that aerodynamic downforce contributes relatively little, rough enough that mechanical compliance matters enormously, and long enough that a car that can maintain consistent tire loading through the entire arc gains a measurable advantage over one that's fighting oscillations. The Midwest setup, which looked catastrophically wrong by every conventional metric, was producing exactly the mechanical stability that corner rewards most. The destructive interference pattern was canceling out the oscillations that normally cost drivers exit speed through long, slow corners on rough surfaces. But one qualifying session doesn't prove anything. Drivers push differently in qualifying than in races. Track conditions are different. Tire temperatures are different. The professional teams filed the anomalous corner speed data away as an interesting footnote and focused on preparing for the race. They had their own problems to solve. The Midwest team, meanwhile, was doing something unusual in their pit garage. They weren't making any setup changes. Every other team in the paddock was adjusting something based on qualifying data. Spring rates, damper settings, tire pressures, anti-roll bar adjustments. The constant iteration that is professional motorsport preparation. Dennis, Catalano, and Washington sat in their garage, looked at their data, and changed nothing. They couldn't. Their entire testing program had identified specific setup configurations where the harmonic balance emerged. Any adjustment, even a small one, would shift the frequency relationships and potentially destroy the interference pattern they'd spent months finding. The setup was either right or it wasn't, and changing it based on conventional instincts would be the worst possible response to data they generated through unconventional methods. Race day at Sebring in March carries its own particular atmosphere. The track has been running races since 1950, and the concrete has stories in it. Bumps that have ended races, patches that have saved them, transitions between surface types that demand respect from anyone who's serious about finishing. The morning air still carries some coolness, but by midday the Florida sun turns the concrete into a heat sink that radiates upward into everything mechanical and human on the circuit. Tire compounds that worked in morning practice are different animals by afternoon. Setup choices that felt conservative at the start feel prescient or foolish by hour 3, and you don't always know which until it's too late to change anything. The start was chaos, as Sebring starts always are. 3 cars made contact at turn 1 in the opening lap scramble, bringing out an early caution that bunched the field and reset the opening strategy calculations for half the teams in the paddock. Dennis was driving the opening stint, and he used the caution period to settle into the car, feeling his way through the setup's behavior on a track surface he'd never driven with these specific configurations. The frequency interaction principle had shown itself on rollers in a barn and in low-profile club races on smooth regional circuits. Sebring was a different environment entirely. Here's the thing about the first 15 minutes after a restart. That's when you learn the truth about your setup. The tires are coming up to temperature. The fuel load is at its heaviest. The track surface is still in its morning condition. Every handling characteristic is at its most extreme, and every weakness is most exposed. Dennis felt something through the steering wheel in those first laps that he'd felt on the rollers, but never quite trusted until that moment. The bumps that should have been upsetting the front end weren't translating through to the chassis the way he expected. The car was moving over the rough sections, the suspension was clearly working, he could feel it doing its job, but the chassis underneath him wasn't reacting. The platform stayed stable while the wheels did what wheels are supposed to do, which is follow the road surface rather than bounce off it. Lap after lap, the times came back consistent. 158.2, 158.5, 158.1, 158.3. The timing screen showed the Midwest Motorsports splits with a regularity that started to attract attention in the paddock around the 40-minute mark. Professional endurance teams have engineers whose entire job is watching timing screens for patterns. Patterns that indicate tire degradation, fuel consumption rates, mechanical issues developing before they become failures. One of those engineers, working for a factory BMW effort running third overall, noticed that the car in 15th hadn't varied its lap time by more than 0.4 in 40 minutes of racing. He flagged it to his chief engineer. The chief engineer looked at the data and told him to keep watching. Meanwhile, the field was doing what fields do in endurance racing, sorting itself out through attrition, strategy variation, and the gradual revelation of which setups had been optimistic and which had been genuinely quick. A Porsche that had qualified 5th was already reporting increased understeer as its front tires came in harder than expected. A McLaren that had looked rapid in morning practice was managing an overheating issue that forced conservative driving. The normal entropy of a long race was beginning its work, slowly separating the cars that could maintain their pace from the ones that had borrowed speed from later in the stint to look good earlier. The Midwest car wasn't borrowing anything from anywhere. Its pace was its pace, and its pace wasn't changing. By the 1 hour mark, still running 15th, but the gap to the leaders had shrunk by nearly 12 seconds without the car getting any faster. Everything around it was getting slower, and the Ligier with its absurd setup and its 3-man barn crew was just clicking off the same lap times it had been doing since lap 3. Now you might be thinking, okay, consistency is nice, but 15th place is still 15th place. Here's what most people don't realize about endurance racing strategy. Position at 1 hour is almost completely irrelevant. Position after pit stops, after the field has cycled through its first round of strategy, after the initial tire sets have come in and revealed their true degradation curves, that's when you start to understand what the race actually looks like. And the first round of pit stops at Sebring that day told a very clear story to anyone paying close enough attention. Professional teams with practice pit crews were executing stops in under a minute. Driver changes, 4 fresh tires, fuel, adjustments. Slick, expensive, impressive. Midwest Motorsports took 2 minutes and 15 seconds. Washington doing tires on one side, Catalano on the other, Dennis climbing out and handing over to Catalano for the second stint. They lost 3 positions in that pit stop, dropping to 18th. But when Catalano rejoined the circuit on fresh tires, something happened that stopped conversations in 3 separate team garages simultaneously. His first lap back was a 158.4. His second lap was a 158.2. The car hadn't changed. The driver had changed. The tires had changed. The fuel load had changed, and the lap times hadn't changed. The BMW engineer who'd been watching the timing screens walked across the paddock to find his counterpart from the Porsche effort. He didn't say anything. He just showed him the timing data on his tablet. The Porsche engineer looked at it for a moment, then looked up with an expression that mixed professional skepticism with something that was starting to look uncomfortably like concern. Two different drivers. Completely different driving styles, different physical characteristics, different levels of experience. One a former professional with years of IMSA seat time, the other a mechanical engineer who'd done most of his racing in regional club events, and the lap times were identical within 0.4 of a second. That wasn't driver talent producing those numbers. That was the car. Here's the thing about what was happening that neither engineer fully understood yet. The frequency interaction setup wasn't just producing consistent lap times. It was producing consistent lap times because it was removing the variables that normally create inconsistency. In a conventionally set up racing car, the driver is constantly making micro corrections, adjusting for the car's changing behavior as tires wear, as fuel burns off, as track temperature rises, as their own physical fatigue accumulates over a stint. Great drivers make these corrections so quickly and intuitively that they look smooth. But the corrections are still happening, and they cost time. Every micro-correction is a moment where the car isn't doing exactly what the driver intended. Every moment of instability is a moment where the tire isn't loaded optimally. Multiply those moments across 4 hours of racing and you understand why lap time consistency is so hard to achieve. The Midwest setup was eliminating most of those micro-corrections at the source. The destructive interference pattern was absorbing the chassis disturbances before they reached the driver as a handling problem requiring correction. Catalano wasn't driving around a problem. He was driving a car that had fewer problems to drive around. The distinction sounds subtle. The lap time data showed it was anything but. By the 2-hour mark, they were back to 12th. The 3 positions lost in the pit stop had been recovered through pure pace consistency, and they were gaining more. A Porsche ahead of them was struggling with brake fade, its driver visibly working harder through the braking zones, the car moving more under braking than it had in the opening hour. And Aston Martin was managing a gearbox that had developed the reluctance to find third gear cleanly. Normal endurance racing attrition, the mechanical and setup chickens coming home to roost as the race wore on. The television broadcast team finally noticed them around this point, though as Washington would later recount with considerable amusement, they got the team name wrong, calling them Midwest Motors in the lower third graphic. But the commentators, experienced endurance racing voices who'd seen hundreds of these events, couldn't quite articulate what they were watching. They noted the consistency. They noted the unusual setup. They mentioned the small team and the limited budget in the way that broadcasts always mention small teams and limited budgets, as human interest color rather than genuine technical analysis. What they didn't say, because they didn't know, was that they were watching a fundamental principle of vehicle dynamics being demonstrated in real time on one of the world's most demanding racetracks. The second round of pit stops reshuffled the order again, and this time Midwest Motorsports lost only 1 position. Their stop was faster, the crew having learned from the first one, and Washington rejoined in 9th place for the final stint. 9 cars ahead of him. 4 of them factory-supported efforts with professional drivers and millions of dollars of preparation behind them. 5 of them well-funded privateer teams with experienced racing drivers who'd been doing this for years. And Washington, a 53-year-old machinist from Ohio who ran his own small business and had learned to race in regional club events on weekends when the shop wasn't too busy. Look, I want to be careful here not to make this sound like pure fairy tale, because motorsport isn't a fairy tale, and Washington wasn't a fairy tale driver. He was a genuinely skilled amateur racer with good instincts and years of experience in his class. He wasn't out of his depth, but he was operating with a different set of tools than the professional drivers around him. Where they were using talent and experience to extract performance from imperfect situations, Washington was using a car that created fewer imperfect situations to begin with. The setup was doing work that professional drivers normally do with their hands and feet and the accumulated intuition of thousands of racing miles. His opening laps and the final stint were, by this point, almost predictably consistent. 158.6, 158.3, 158.1. The track was different now than it had been at the start of the race. Hotter, more rubbered in, the concrete having expanded in the afternoon sun in ways that changed the bump characteristics at specific corners. Cars that had been well set up for morning conditions were fighting an afternoon track that their setups hadn't anticipated. Teams were making what adjustments they could during pit stops, chasing moving targets with limited tools and limited information. The Midwest car, unable to make adjustments without destroying its harmonic balance, was accidentally doing exactly the right thing. Its setup was less sensitive to the changing conditions because the frequency interaction principle was absorbing those changes before they manifested as handling problems. This is where it gets really interesting, because what happened next wasn't dramatic in the Hollywood sense. There was no single moment of overtaking brilliance, no desperate last-corner lunge, no rain shower that reshuffled everything. What happened was more interesting than that. What happened was mathematics. Pure, patient, relentless mathematics. 7th place had a tire issue and pitted unexpectedly. 6th place was managing an electrical gremlin that forced conservative driving. 5th place, the Mercedes that had been impressively quick all afternoon, was now reporting that the car felt unpredictable, its driver using the radio to describe a front end that was behaving differently in left and right-hand corners. A classic symptom of differential tire degradation on a circuit with more left-hand corners than right. With 40 minutes remaining, Washington was running 6th. With 30 minutes remaining, he was 5th. The Mercedes having slowed enough that he went by without a fight on the back straight. 4 factory-supported efforts remained ahead of him. The paddock was paying full attention now. Engineers who'd been focused on their own cars were watching the timing screens with the particular intensity of people who've just realized they may have made a significant professional miscalculation. The Porsche engineer who'd given that presentation in the morning, the one using the Midwest telemetry as a teaching tool for what not to do, was standing at the pit wall of his team's garage staring at data that contradicted everything he'd said 6 hours earlier. Then came the moment that the endurance racing community would talk about for years afterward. The 4th-place Porsche, running a professional driver with a championship to his name and a car prepared by one of the most experienced teams in the paddock, caught Washington with 20 minutes remaining and made a move into turn 1. Clean, professional, exactly the kind of pass that professional drivers make against amateur competition. Washington didn't fight it. He gave the position cleanly, settled back into his rhythm, and started doing something that the Porsche driver and his engineers didn't immediately recognize as a threat. He started driving his corners. Specifically, he started driving the carousel the way the car's setup allowed him to drive it, carrying more minimum speed than anyone else on the circuit, getting on the power earlier on the exit, using the stability that the frequency interaction principle provided to run a line that the conventionally set up Porsche simply couldn't replicate. The Porsche was faster in Sector 1, where power and aerodynamic efficiency dominated. Washington was faster in Sector 3, where the rough, slow corners rewarded mechanical grip and chassis stability above everything else. Lap after lap, the Porsche would build a gap in the first sector, and Washington would recover it in the third. The net result was effectively 0. They were lapping within a tenth of each other, which meant that Washington, starting from slightly behind, was slowly reeling the Porsche back in. The Porsche engineer on the pit wall recognized what was happening before his driver did. He got on the radio and told his driver that the privateer behind him was faster in the final sector, and to protect the inside line through the slow corners. The driver acknowledged and tried to adjust, but here's the problem with trying to defend against a car that has a genuine setup advantage in specific corners. You can defend the line, but you can't defend the physics. With 15 minutes remaining, Washington was right behind the Porsche. With 12 minutes remaining, he was alongside it through the carousel, both cars running at their limits, both drivers fully committed. The Porsche took the orthodox line, the one that every textbook and every coaching session said was correct. Washington took a wider entry, carrying more speed, trusting the setup stability to let him rotate the car through the corner in a way that his opponents couldn't safely replicate. On the exit, he was ahead by half a car length. Down the following straight, the Porsche pulled alongside on raw power. Into the next braking zone, side by side, both drivers fully committed, neither willing to yield. The final 10 minutes of that race produced something that endurance racing rarely delivers, cleanly. Not a dramatic crash, not a safety car controversy, not a strategic masterstroke from a pit wall genius. Just two cars, one built by a factory program with decades of accumulated expertise and unlimited resources, one rebuilt from a crash by three guys in a barn with borrowed equipment and unconventional ideas, racing each other on pure merit around one of the world's most demanding circuits. The Porsche had more power. Washington had more corner speed. Neither advantage was decisive enough to create a clean break. Lap after lap they swapped fractions, traded tenths, pushed each other to the absolute limit of what their respective setups could produce. And here's what made it genuinely extraordinary, beyond the David versus Goliath narrative that the television commentators were enthusiastically constructing in real time. Washington wasn't really racing the Porsche, not in the way that professional drivers race each other, reading opponents, managing tires strategically, making calculated decisions about when to push and when to conserve. Washington was doing something simpler, and in many ways more impressive. He was just driving his laps. The same 1:58 seconds he'd been producing since the first stint. The same lines, the same reference points, the same commitment level, corner after corner, lap after lap. The setup was so consistent, so predictable, that he could place the car in exactly the same spot on the circuit with a repeatability that professional drivers spend entire careers trying to achieve and rarely fully reach. The Porsche driver was the one doing all the work, fighting tires that had given their best performance an hour earlier, wrestling a chassis whose behavior had shifted as fuel load changed and rubber wore, making the constant micro-corrections that a degrading setup demands from even the most talented hands. He was driving brilliantly under the circumstances. The circumstances were just harder than Washington's, and the gap between them, measured in pure effort required to maintain pace, was widening with every lap even as the gap measured in seconds remained stubbornly close. With 5 laps remaining, Washington made the decisive move. Not a lunge, not a desperate gamble. He simply drove deeper into the braking zone at turn 10, trusted the setup's stability to let him trail brake later than the Porsche could safely follow, and came out of the corner with enough momentum advantage to reach the following straight ahead. The Porsche driver made one last attempt to respond, pushing beyond what his tires could cleanly support, feeling the front end wash wide on the exit of the following corner. He caught it. He always would. He was too good a driver not to, but catching it cost him 2 tenths, and 2 tenths against Washington's setup advantage through the final sector was enough. Across the line, 5th place. Midwest Motorsports Dynamics, the 3-man barn crew with the wrong setup and the borrowed dynamometer, had finished 5th overall in their first serious race against factory-supported professional competition. The paddock reaction was immediate and fascinating in the way that professional communities react when something challenges their foundational assumptions. The initial response was skepticism dressed as analysis. Engineers descended on the Midwest pit area with questions that were really disguised attempts to find the conventional explanation that would make the unconventional result make sense. Was there a weight advantage they hadn't noticed? Had the officials missed something in scrutineering? Were the timing screens showing something anomalous? Dennis answered every question patiently and honestly. No weight advantage. Clean through scrutineering. Timing data was accurate. The car was exactly what it appeared to be, running exactly the setup the data showed. The questions gradually shifted from skeptical to genuinely curious, which is the sound of smart people updating their priors in real time. The Porsche engineer who'd given the morning presentation sought Dennis out personally that evening. The conversation, by multiple accounts from people who were nearby, lasted nearly 2 hours. The engineer was technically sophisticated enough to understand the frequency interaction principle once Dennis explained it, and intellectually honest enough to recognize immediately what it implied about the analytical frameworks his team had been using. He didn't minimize what he'd witnessed. He asked detailed questions, took notes, and before leaving told Dennis that what he'd seen that day would change how he thought about suspension setup for the rest of his career. It was a generous thing to say. It was also almost certainly true. But here's what happened next. And this is the part of the story that I think matters most. The part that separates this from being merely a great racing anecdote and makes it something genuinely significant. Within a week of Sebring, Dennis received consulting offers from 3 major teams. Catalano was approached by a suspension manufacturer interested in commercializing the resonance mapping methodology. Washington had orders for custom fabrication from teams wanting to experiment with similar configurations. By any conventional measure of success in motorsport, they had arrived. The garage operation had produced results that opened doors to the professional world they'd been locked out of. And they turned all of it down. Now you might be thinking, that's insane. Why would 3 guys who'd spent everything they had proving a concept walk away from the professional validation and financial reward that concept had earned them? Dennis explained it in an interview that got very little attention at the time but has been quoted extensively since. He said that what they'd discovered was too important to become a competitive advantage for whichever team could afford to hire them. If it was going to change racing, it needed to change all of racing, not give another already well-funded program another edge over the privateers and gentlemen drivers who made up the majority of the sport's participants. So instead of taking the consulting contracts, they published everything. Not in a peer-reviewed journal, not in a technical paper behind an expensive paywall, on a free website, written in language that a mechanically minded amateur could understand, complete with their full data set, their methodology, their theoretical framework, and enough practical guidance that anyone with a car, some accelerometers, and enough time could start exploring frequency interaction tuning for themselves. The response from the established motorsport engineering community was not uniformly positive. Several prominent race engineers published detailed rebuttals arguing that the Dennis Catalano effect, as it was already being called informally, was either misunderstood by its discoverers or represented such a narrow and specific phenomenon that its practical applications were limited. The suspension manufacturers, whose products were built around conventional setup philosophy, were particularly vocal. Here's what most people don't realize about industries built on accumulated expertise. The threat isn't always from outside. Sometimes the most dangerous challenge to established wisdom comes from people who were inside the system long enough to understand it deeply, left involuntarily, and returned without the psychological investment in protecting it. The privateer teams who had nothing to protect and everything to gain moved fastest. Within 6 months of the publication, variations of the resonance mapping methodology were appearing in club racing paddocks across North America and Europe. The configurations were different in every case, because the principle required individual testing for each specific car on each specific circuit. But the approach was consistent. Stop optimizing individual parameters toward theoretical ideals. Start mapping the setup space for harmonic interactions. Find the pockets of stability that conventional methods couldn't see, and build your race strategy around the consistency those pockets produced. Results followed. Not always dramatically, not always in ways that generated headlines, but consistently enough, in enough different cars, on enough different circuits, that the pattern became undeniable to anyone willing to look at the data honestly. The major factory teams eventually adapted, as major factory teams always do when confronted with a principle that demonstrably produces results. Mercedes developed a computational model that could predict frequency interactions across a car's setup space, though it required processing power that made it impractical for real-time use at the circuit. Ferrari created active suspension systems that could adjust harmonic relationships dynamically during a stint, essentially automating the process that Dennis, Catalano, and Washington had discovered through months of manual testing. Red Bull brought Catalano in as a consultant, working remotely from Ohio on a retainer that allowed him to keep his agricultural engineering practice running alongside his motorsport work. He insisted on both. He said that staying connected to the agricultural world was how he'd found the insight in the first place, and he wasn't going to lose that connection for the sake of a more conventional consulting career. Midwest Motorsports Dynamics raced 3 more times after Sebring. A DNF at Watkins Glen when a half-shaft failed on lap 40, entirely unrelated to the setup, just bad luck and a component that had been stressed beyond its limits during the Sebring race. A midfield finish at Road America where the setup's advantages were less pronounced on a circuit with long, fast corners where aerodynamic efficiency matters more than mechanical stability. And then Mid-Ohio in the rain, where everything came together in the way that occasionally happens when the right car meets the right conditions at the right moment. In wet conditions where mechanical grip is the only grip available and aerodynamic downforce from most sports cars becomes largely irrelevant, the frequency interaction principle's stability advantages were amplified beyond anything their testing had predicted. They won outright. Not their class. Outright. Against a full field of professional teams in a proper race, in conditions that stripped away every advantage that money and factory support normally provide, the barn crew from Ohio was simply faster than everyone else. Then they stopped. The decision was made quietly and collectively, without drama. The business meetings were multiplying. The sponsor calls were becoming harder to ignore. The simple dynamic of 3 people who trusted each other completely, working on a problem they'd defined for themselves, was being diluted by external interests that each had legitimate reasons to pursue, but that collectively were transforming what they'd built into something different from what it had been. They sold the car to the International Motor Racing Research Center at Watkins Glen, where it sits today with 2 plaques. The first lists the specifications. Front springs 800 pounds per inch. Rear ride height 80 mm. Front anti-roll bar disconnected. Numbers that still produce visible discomfort in engineers who see them for the first time and understand what they mean. The second plaque carries Dennis's quote, "The one that's been reproduced in engineering school curricula, and conference presentations, and online discussions ever since. We didn't prove that conventional wisdom was wrong. We proved that unconventional wisdom could be right." The Dennis Catalano effect is taught now in vehicle dynamics courses at several engineering schools. The resonance mapping methodology has been incorporated into the curriculum at racing academies that a few years ago would have dismissed it as fringe thinking. Motorsports regulatory bodies have had to revisit setup parameter windows that once seemed comprehensively defined, because the frequency interaction principle revealed that some of those windows were excluding potentially faster configurations for no reason beyond the fact that nobody had tested what lay outside them. The playing field hasn't been completely leveled. It never will be. Money still matters enormously in motorsport, and the teams with the biggest budgets have found ways to exploit the Dennis Catalano effect more thoroughly than any privateer could afford to. But the understanding has changed. The assumption that conventional setup optimization represents the complete solution space has been broken permanently, and that matters more than any single race result. Dennis still works as an independent suspension consultant, exclusively with underfunded teams. He charges less than the market would bear because the point was never the money. Catalano split his time between agricultural engineering and motorsport consulting until recently, when he joined a university research program studying suspension dynamics in emergency vehicles, applying racing principles to machines where consistency and predictability under extreme conditions can mean the difference between life and death. Washington still runs his machine shop in Ohio. Half his business now comes from racing teams wanting custom fabrication work. He races occasionally in regional events, in a car he built himself, set up using the resonance mapping methodology, lapping with the kind of metronomic consistency that makes his competitors check the timing screens twice. The next time you're watching an endurance race and the camera finds a car that looks wrong, riding too high, rolling too much, doing things that your pattern recognition says shouldn't produce competitive lap times, pay attention to the timing screens. Watch the consistency of that car's splits over the course of a stint. Watch whether it maintains its pace when everything around it is degrading. Because somewhere in motorsport right now there are people in a garage who can't afford to think conventionally, who are being forced by circumstance into the kind of creative problem solving that occasionally produces something the established world missed entirely. The biggest barrier to innovation in any field isn't technology or money or talent. It's the assumption that the way things have always been done is the way they must be done. 3 guys in a barn in Ohio prove that assumption wrong, and the sport has never quite looked at a suspension setup sheet the same way since.